Okay, so I'm going to be discussing today the wave equation. I'm going to be giving a derivation of the one-dimensional wave equation. I'm not going to give you the derivation of the two- or three-dimensional wave equation, but I will tell you what it is. Probably you'll be able to anticipate what it is after I give you the one-dimensional version. So the situation that we're modeling here is we have an infinite length string. So we'll just imagine the dot, dot, dots. We're coming in from minus infinity, and we look at this portion, go out to positive infinity. So here we are with the string in its neutral position. We want to imagine if we start this with a certain profile and let go of it, what's going to happen to the string. We want to imagine what happens if we hit it with a hammer, then how will the string vibrate? And so we want to find a partial differential equation. Well, I should say initially we don't know, if we're just coming into this, maybe it's not going to be a PDE that we have. Maybe it'll be an ODE, or maybe we'll just get a formula directly for it. But as you'll see, we're going to get a PDE that models the behavior of this string as time goes on. Okay, so we're going to let's introduce a few variables here. So let's say we have this string, and it kind of, at a certain time, its profile looks like this, let's say. The distance, the displacement, it goes off like that. U of xt is going to be the displacement, which I'm going to abbreviate as this displacement from the neutral position. Okay, so like this height, if this is x, this right here would be u of xt. Okay, the displacement from neutral at location x and at time t. So like this would be a negative number here since it dips below the axis. Okay, and I'm actually going to need this, so I'm going to erase this part carefully, hopefully. But, f sub v of xt. Okay, so what is this? Again, let's say I look at a generic position x, f, the force vector f, so not fv, but f is going to be the force at location x from the left-hand part of the string. So f is going to be the force, vector at location x at time t of the left-hand part of the string acting at the location x here. And fv is the vertical component of f. So this is the vertical component of f. Okay. So I guess this is, maybe I should write this here. So vertical component of the f vector. And again, f is the force at x from the left-hand part of the string. Okay, now another assumption here that I'm going to make that I haven't made yet, but it's going to let us only care about the vertical component here, is we're going to assume there is no horizontal movement. We're going to assume that there's no horizontal movement. So in other words, the points are only going up and down. Now, I would be interested, for anybody, but I think maybe the engineer, the people who have experience, engineering might be able to talk about this more. When you look at vector versions of the wave equation, you consider horizontal displacement as well, and then things get very complicated when you start looking at that. Okay, I don't know if anybody's had any experience dealing with that. And I think this is where you get things like stress and strain and stuff like that I'm not an engineer, so I don't think a whole lot about, so I don't have a great intuition in it. Okay, so this is the setup here. And what I want to do is I want to take a generic point. I'll just use this same point here and call it A. So this is now going to be A, and then another generic point, I'll call it B. I'm going to look at this representative segment of string. A and B are arbitrary. And I want to compute the forces acting on, in this string two different ways. The first way, if I can integrate from a to b, if I integrate from a to b, the function m of x times the double partial derivative of t. What am I going to get here? M of x is the mass density. So mass density times dx gives me mass, and then that is acceleration. So this is force times, or the mass times acceleration. So this will give me the forces, at each point on this string. But there's another way that I can compute this. So there's another way that I can compute, this is the force here, but there's another way I can think about the force. I can look at the portion of the string from A to B as being kind of one isolated thing, and then what are the forces acting on the string going from A to B? Well, it's going to be the portions from the left, the force from the left-hand part of the string, the force from the right-hand part of the string, plus any external forces that might exist. The external forces, I'll go on ahead and write what that is right now. This is going to be the integral from A to B, m of x, q of xt, dx. And what is this? Well, again, mass, m is mass density, so m times dx gives us mass. So this is external force per unit mass. Okay, so this would be something like minus g if we're looking at gravity. All right. On the other hand, if I look at the force at A from the left-hand part of the string is just going to be equal to this vertical component, like that. Just a vertical component of this vector. It's the rest of the string pulling this way. But I need to be a little more careful. If I look at B, F is this vector, and F sub V is the vertical component of that vector. But at B, this vector is the force of the string to the left of B. But if I want to look at the force of the string from the right, this isn't the right thing. However, Newton's third law says this is just equal to minus F, because equal opposite directions. All right, so now what this tells us is that this is going to be minus F sub V at PT. Okay. Well, maybe we can think about fundamental theorem of calculus here, because this I can write as minus the integral from A to B of the x derivative of F. And then plus this integral here, but it's all, we're all integrating from the same distance here, so it's going to be in the same thing, the same dx for both of them. So it's going to be m of x q of xt dx. Whoa. All of this is multiplied by dx. Well, these are all equal to each other. So I've got an integral from a to b of m times the double t derivative of u equals this integral. A and b are arbitrary. Sorry, I just realized if I have the minus sign here, I need to put it there. It doesn't need to hit that part. Okay, so now what this tells me then is mass, the mass density, times the double t derivative of u is equal to minus the x derivative of f plus m times the external force density. Density meaning force per unit mass. Okay, so what I'm going to do now is I'm basically going to write this equation over here, and my computer's doing the thing where it falls asleep. I'm going to write that equation, this equation over here, and then erase everything over here, because what I need to do is I need to figure out how to write f sub v. Sorry, there should be an f sub v here and here. I need to figure out how to write that in terms of u. So I've got m times the double t derivative of u is equal to minus the x derivative of f plus m times q. Okay. f sub v, f sub v, my claim, and I'm not going to justify this too much, is that this is a function of the x derivative of u. So let me explain why that might be true. So let's think about this point here, A. I've got the string kind of going through this point right here. If the string has a higher x derivative, it means it's more like this. Okay, if it's more like this, it means there's going to be more force pulling down than otherwise. Okay, so what this tells us then is that it is a function of the x derivative of u. Okay, how does that help us? Well, the next thing that I'll say, which might not be clear why it's helpful yet, is I'm going to say f of 0 is less than 0, and I'm just going to call this like it's going to depend on the material at a certain point. So I'm going to call it k, little k, but know that it also depends on the material at the point. So whatever point we're analyzing this at, it depends on the material there. Okay, why is it negative? Well, if the derivative is positive, it means the string is like this, which means the portion of this string over here is pulling down on it, okay, which is in the negative direction. So f prime of 0 is less than 0. Okay, well now how does that help us? Now maybe we can see about how that helps us. So let's think about f of epsilon, where epsilon is going to be very small. So we're going to be plugging in the x derivative of u there. And if you think about a guitar string, like this is not what the profile of a guitar string looks like, right? A guitar string, this is a very exaggerated thing, very exaggerated picture of what happens to a string. Typically, a string is just going to vibrate just a little bit. In other words, the x derivative typically is going to be very, very small. Okay, so f of epsilon then, we can look at this a couple of ways. I'm going to look at it in a Taylor series way. This is going to be equal to f of 0 plus f prime of 0 times epsilon, and then what we're going to have here would be f double prime of 0 over 2, and then it's going to be times some c. This is in between 0 and epsilon. Okay, but if epsilon is very small and c is in between 0 and epsilon, this term here is negligible. Why? Well, you know, if epsilon, if c is small, then you square it, it's equal to 0. This is the fluxion thing that Newton did. It's a very, okay, obviously it's not literally equal to 0, but it's negligible in the sense that it's much smaller compared to these two terms right here. Okay, this is just Taylor's theorem, by the way. You can either think about this as Taylor's theorem or just think about it in terms of the mean value theorem. However you want to think about it, the point is we get the approximation for small epsilon, f of epsilon, is approximately equal to f of 0 plus f prime of 0 times epsilon. Okay, now what is f of 0? Well, if the string is flat, it's not being pulled down there. So f of 0 is going to be equal to 0. And so this is equal to, sorry, I should have put a minus there. If I want k to be positive. So this is going to be equal to minus k times epsilon. Okay, so now what does this tell me then? It tells me that the vertical component of f is roughly equal to minus k times the x derivative of u. So now what I have over here is this. I've got two minus signs, that'll cancel. I'm going to have the x derivative of k times the x derivative of u plus nq. Okay, and again, let's just explicitly state here that k can potentially depend on x. Okay, so now there are various ways. This is not, if you think wave equation, this is not what most people are going to think of when they think about the wave equation. So let's look at two things. If if Q is negligible, in other words, it's approximately equal to 0, like you don't typically, I'm not a musician, but I don't think musicians worry about the force of gravity on their guitar strings, just kind of neutral. Okay, so if Q is approximately equal to 0, or exactly equal to 0, we can forget about this term, and the equation becomes M times the t derivative of U is equal to X times K times the x derivative of U. If K is constant, then we can write this as the double t derivative of U is equal to K over M times the double x derivative of U. Because if you move the K out, then you just have the double x derivative of U. And typically, this number right here, since K is positive, that's why I wanted it to be positive, and M is positive, this is typically called C squared. This becomes the t derivative of U is equal to C squared times the x derivative, the double x derivative of U. Okay, and why are we calling that C squared? Well, a number of reasons. K over M is positive, and so if I square a real number, it's definitely going to be positive, even if I don't know anything else about C. But I think maybe a more important reason is that we will see, or maybe you will see in the exercises after I show you how to solve this using Fourier transform, which is just one way to do it, that this is going to, this parameter C is going to be an important part of the solution. Okay, so this is the one-dimensional wave equation. I'll just say, by the way that I derived it is not the way that most textbooks derive it. I followed the outline in a book by Lawrence Evans that basically works on this thing here, where that uses these ideas here. It's not how most textbooks do it. I just wanted to point that out. I think it's good to see different things. Okay, the last thing that I want to mention is that in higher dimensions, you get something very similar to this. In higher dimensions, you're going to have something like M times the t derivative of U. Okay, just wherever I see the x derivative, I'm going to replace this with a gradient in these spatial variables. So if it's in 2 dimensions, this will be a gradient in the xy variables. Okay, so it's going to be this dotted with k times the gradient of u, and then plus mq. And then again, we can make all of these various statements that we did over there. If q is 0 and if k is a constant, we can write this as the double t derivative of u is equal to c squared times Laplacian. Again, because gradient dotted with gradient gives us the Laplacian. This would be the 2 or more dimensions. So this is 1 dimension, and this is basically in general in dimensions. Just as long as you realize by Laplacian in 1 dimension, you just mean the double x derivative. Okay, we're going to I'm going to use Fourier transforms to find a solution to this. It's a very common solution. You can derive that solution more ways than Fourier transforms, but that's kind of what we're doing now. So I'm going to do Fourier transforms for that. It's actually very, finding solutions to the wave equation in higher dimensions, it could actually get very complicated, or it is very complicated. It doesn't get very complicated. It is very complicated. The book that I referenced earlier by Lawrence Evans, it's a classical PDE book. You can look at that, and it has the derivation of solutions in higher dimensions. Okay, that's it for this video.